Okay, good afternoon. I'm sorry. Oops. The sound quality is good. Okay, so today we're going to just continue what we were talking about on multi-threaded kernels. So in the previous lecture we started talking about context switching between two threads. So let's start from there. So we're writing a function that is a kind of a weird function. So first of all, who's gonna run this function? It's important. This function is going to be called, or it's going to run at kernel mode. So this is part of the kernel code. Now we're going to get into this function in the context of a function, in the context of a thread, and we're going to get out of it in a context of another thread. Now you have to ask yourself, this is probably the most important thing that you have to ask with this regard. What does it really mean to run a function in a context of one thread and running the same function in the context of another thread? And if you dig into that question, the answer to that question, you realize that really what matters is the stack. The code is the same, but the stack is different. And the stack is the one that matters the most because our variables are on the stack, our return function, our return addresses are on the stack. So basically, when I say we get into this function in the context of one thread, what I really mean is we start running this function while the stack pointer is pointing to the stack of thread A. And then when we get out of it, the stack pointer is now pointing to a separate stack. So therefore, we're running this same function in a context of another thread. Now let's get into this. Now, if you want to context switch between threads, the first thing you have to do is to save all the registers. Because you're going to context switch to some other thread, and that other thread could do whatever they want to the registers, and you might lose the context. So the first step is to push all the registers. Where do we push them? We push them to the stack, to the kernel stack of this old TCB. So now we kind of saved all the registers. What do we do now? We have a stack pointer right now. So the SP, this is the register in the processor. So this is a register in the processor. Let me make this a little bit better for myself to write. So this is a register in CPU. Now this guy is pointing to the head of kernel stack of old TCB. Let me actually call this guy old thread. It's better that way. Use me. Okay, so the SP register is pointing to the stack pointer of the old thread. Now, we're going to now switch to the stack of kernel stack of new thread. That we want this to now point to this guy. So before we make this change, before making SP register to now point to the kernel stack of the new thread, we need to save this, because if we don't save it, we don't know where the head of the stack was for this old thread. Now, where do we save this? We save this in the TCB of the old thread. So we just say old TCB SP. So this basically is a field in TCB struct. So this is a field. We say the value of this should be equal to SP register. So wherever SP is pointing, basically this address, X, 00F0 whatever, we put that in the old TCB. We save it. Now we know where the head of the kernel stack for this old TCB was, for this old thread that we want to context switch from. Once we do this, now we need to point to the head of the stack of this new thread that we want to context switch to. Where do we get that? Hopefully we have it in the new TCB SP. So hopefully we have saved this address in the TCB of the new thread, so we can now read it. So then next line becomes SP. Now we're changing the register. We're saying SP register, you have to now point to this new TCB SP that I saved previously. So now I have done this change. Now this SP is pointing to this register, and I have saved that one. Now context switch has happened, almost. Now what do we do next? Hopefully we have saved the state of this new thread that we're going to. Previously, last time we context switched from that thread, we hopefully have saved the state of that thread, meaning that we have pushed the registers to the kernel. Now we can read it. So then we pop all the registers from the kernel stack of this new thread. And now we're ready to return. Where do we return? This is a very important question. If you remember, return address was saved on the stack. So if you go back to one of the, I think it was the probably lecture 2 or 3 where we talked about stack, the return address is always on the stack. Which stack? This is a stack, because now a stack pointer is pointing to the kernel stack of the new thread. So wherever we have it here, like the return address, we're going to return to that address. Okay, now I have to remove everything I have here because I'm going to use this space for the slide. So hopefully you got everything that I said. Now I'm going to just kind of pose some questions. Let's look at it. So first of all, this new TCB, this new thread that we want to context switch to, could be 2 types of threads. The first type is a thread that we previously context switched from, and now we're context switching back to. So that's type 1. The type 2 is a thread that we have never ever ran before. So this is a newly created thread that we just want to start running it. So that's type 2. So keep that in mind. We can have these 2 types of threads that are fresh, we never ran them before, and threads that we previously ran and context switched from, and now we want to context switch back to. Now, why is that important? Well, it's important when we are popping from this stack, right? So when we context switch, when we change the stack pointer to this new TCB SP, we're going to pop from this. Now, what are we popping? Now, the question is, what is being popped from this stack? Now, that depends on what kind of thread we're dealing with. So if this is a thread that I ran before, so if this is not a newly created thread, then at some point when I context switched from this thread, I pushed the registers. So now I'm popping the same things that I pushed. So good, I'm fine. Previously I pushed a bunch of stuff on the stack, now I'm popping them. What if this new thread is a newly created thread, a thread that I've never ran before? So in that case, we have to be careful because we're still going to run this code. And this code expects to see stuff on the kernel stack. This means that when we're going to create this thread, when we're going to create a new thread, we have to push some dummy data on that stack because we know that they're going to be popped here. So this is the important piece that we're going to come back to. When we talk about creating new threads, we talk about this dummy data frame. We need to put it because when we context switch to this guy for the first time, we're going to pop stuff from the kernel. So there has to be some stuff on the kernel. And at this point, they could be just dummy data because we haven't ran this. So the registers, we can just initiate them all to 0, for example. The other question is, where does this return, right? And as I said, it's going to return to wherever address is on top of the stack. Now, if this thread, we had ran it before, and now we context switched from it, and now we want to context switch back to it, we're going to go wherever this thread switch function was called in the context of that thread. So at some point, I was running that old thread, and then let's say timer interrupt went off, or let's say this thread called system call or something. And at that point, I decided to context switch. So I called thread switch. When I called thread switch, what happens is I'm pushing the return address of wherever I'm calling this function thread switch on the kernel stack. So when I return, I'm going to go back to where I called this thread switch. So everything is fine again. So if this new TCB is something that I ran before, I shouldn't worry. There is a return address on the kernel that I'm going to go there. But if it is a newly created thread, then I have to be careful. I have to push the address of where I want to return to here. So where do I want this thread switch to return if this new TCB is a newly created thread? I potentially want to, jump to where I want to run this new thread, whatever function this thread wants to run, but it has a little bit of it's a little bit tricky here. We'll talk about it in the next slide. So I got a question. So as you might imagine, this is absolutely a really simple code, but as you see, it has a little bit of trickiness in it because of how it works. We get into it in the context of one thread, and we get out of it in the context of another thread. So that's why I'm, spending some time so that you actually understand this. Okay, I got a question. How would this work if there was only one kernel stack for all threads? That's a really good question, and it would still work, right? It would be different. So I wouldn't be saving stack pointers stuff, probably. It would be tricky. So this code is designed for the case where I have separate stack pointers for each thread. It would be different, definitely different code if the assumption is I have a single kernel stack for all threads. So I'm not talking about that here. So thank you for the question. This design, this code in front of you, is for the case where each thread has its own kernel stack. If they all had the same kernel stack, if kernel had a single stack that it was using for everyone, the code would be different. And I don't want to go into the details of that because that would be of its own discussion. We would have to have a code and then discuss that. Okay, so now let's talk about this entry point of threads. So as I said, if we're now talking about the return, right, in the thread switch, where do we want to return if it is a newly created? Now, if this thread, this new thread that we want to context switch to, is a kernel thread, then we can just go to the entry point, just jump to the function that this thread is supposed to run. And why can we do that? Because we are already in kernel mode. If you remember the start of this slide, previous slide, I said we're running this code in kernel mode. Now, if the new thread is also a kernel thread, so we're not going to change the mode, then everything is fine. We can just push the address of the function that this thread wants to run on the stack. So when thread switch pops the return address, it just jumps to this function and starts running it. All good. However, if we want to, if this new thread, this newly created thread that we want to context switch to is a user thread, then we can't just simply return to the beginning of the function that it wants to run. Because if we do so, we're going to start running that function in kernel mode, because the mode of execution right now is kernel. So we require a mode switch. We need to switch mode when we jump to that function. Now, I believe in your labs, we have this special function if things haven't changed from 2 years ago that I taught this course. So there was this function that we would, when we create these new threads, then we jump there, and that function then jumps to the beginning of the function that you want to run and also do a mode switch. So you can have this special kind of function that you use to do a mode switch. In that case, you just push the address of that special function. When you create your new thread, you push the address of that guy on top of the stack. If not, you can actually use this handler function that we saw. If you remember, I talked about this system call or interrupt handler, and at the end of it, we have this special kind of return where we kind of return and change the mode if necessary. If from where we came was a user mode, then we switch to user mode. If it was a kernel mode, we don't switch anything. So we could use this address kind of, and then push whatever this needs to pop, and then push the address of the function that we want to return. And therefore, this return will jump to that function, and it also changes the mode for us. So we can use this for our special function that would do a mode switch and also jump to the function that we want to run in this thread. So let's see how that works. So let's now look at the code for creating a new thread. And I'm assuming that here I'm creating a user thread, because as I said, if you're creating a kernel thread, it's a little bit different because you can just push the address of the function that you want to start executing to the top of the stack. But if it is a user thread, we're going to push the address of the handler. Now, let's see how it works. The first thing I do, I create a TCB. Then I allocate a stack for this. This is a kernel stack. And please note that I'm adding this stack size because the stack, stack grows downwards. So you need to go to the higher address and then go down. So basically a stack goes down, like whenever you want to write to a stack, you do this. Whatever you want to write, let's say you want to write a number. So you do a star minus sp equals 2 to write to sp. So sp pointer is basically decreasing as the stack grows. So that's why I'm adding this. Now we need to set up the kernel stack. Two things are important if you remember from that context switch. The first one was the dummy data that we have to push, because the thread switch expects to see those registers. It's going to pop them. So that's the last thing we're going to push, because that's the first thing it's going to be popped, right? So we're going to push in the reverse order. So the last thing we're going to push is the things that thread switch wants to pop. Then after it pops, it's going to go to that exit handler, and exit handler is going to pop a bunch of registers, right? So if you remember when I was talking about the handler, I said you have two options: either push all the registers and be free to use all those registers, or just push the registers that you are going to modify. So you can have a convention that says, in my handlers, I'm going to just use 3 registers. Then your handler is expecting to pop 3 registers. So we need to push that. And then the last thing is the address that your handler is going to pop to jump to that address. So if I write it down, first thing that was going to be popped, the first thing that is going to be popped in kernel switch is the dummy stack, dummy data in thread switch. Then we're going to go to the and then there is going to be an address of the handler, right? That sorry, the last thing, let me wrap my head around. Yeah, so that then it's the address of handler. This guy is going to be popped. Then we go to the handler. The handler is going to pop the registers in handler. And fourth is address of entry point. We're going to jump there. So now we want to create the stack pointer. We're going to push in this order. So the first thing we push is the address of entry point. So we push the arguments and the function that we want to go to. So that's 4. Then we push. Sorry, I should have changed the slides. Here, excuse me. So my slides are messed up. So here I should do star minus tcb sp equals handler. Handler exit. So the address of handler. So that would be the. Oh, so sorry. It's no. My slides are correct. I apologize. I'm probably making people confused. I apologize. So yes. So the third one that I'm pushing. So sorry, the next one that I'm pushing is exactly the registers for the handler. And then I push the address of exit. And lastly, I push the dummy thread switch. So let me put the numbers here. This is 2, this is 3, and these are 4. So again, this is the events that are going to happen right after this thread runs. I'm going to first push a bunch of stuff in the thread switch. Then I'm going to jump to the handler. The handler is going to pop a bunch of registers, and then the handler is going to return. So these are the events that are going to happen in this order. So now that I'm setting up the stack, I just push this in the reverse order. So I first push the entry point, then I push the registers for the handler, then I push the address of handler, and then I push the dummy thread switch frame. And that's pretty much it. I set the state of this thread to ready because this is now ready. I just created it. I believe in your labs, we have 2 types. There is a new type and there is ready type. So if it is a new thread, we set the state to new. But here I'm just treating all of them as ready. So when I create a thread, I make them ready and I put it there. And that's pretty much it. I add it to the ready list and we're done. So we have created a new thread. And these steps are necessary to set up the stack, the kernel stack of this thread, given that these are the things that are going to happen to this thread when it starts running. I hope I didn't confuse you. Or if you're confused, I hope when you rewatch these lectures, it goes away. Okay, I have a question. The implementation for thread switch seems similar to processing switching. What is processing switching? Why is thread switch more efficient than process switch? Oh, I guess I had this discussion once. So let me address that question this way. Depending on the unit of execution in your system, you're going to context switch between those units. Now, if you have a multi-threaded kernel, that unit is thread. So you're always context switching between threads. Now, 2 threads might belong to the same process. So you're context switching between 2 threads from the same process, or they could belong to different processes. So when you context switch from thread 1 of process 1 to thread 1 of process 2, it's as if you're context switching from process 1 to process 2. But again, because the unit of execution is threads, we're always context switching between threads. In older Unix systems where there was no notion of thread, so each process had a single thread and the unit of execution was process, then we would be talking about context switching between processes. But in these slides, we're talking about multi-threaded kernels. So we're talking about basically we're talking about context switching between threads. Okay, so do you mind going over why we need the dummy handler frame and dummy switch frame? Right. So the reason we need them is because when this thread runs first time, so we're creating this thread, and at some point we're going to context switch to this thread, right? So what does it mean context switch to this thread? It means that we're going to start running it inside thread switch, because thread switch was the function that context switches, right? And right, if I go back to this thread switch, here is where we're going to set the stack pointer of the CPU to point to the kernel stack of this thread. Now, this is a newly created thread. Now, the next line that is going to execute is going to pop a bunch of stuff from this stack. So that's where we need to push the dummy switch data. So because then the code is going to pop stuff, so we need to push. Then we're going to return here and I said we're going to return to the handler because we need a mode switch. Now, when we go to the handler, if I go back to the handler code, the handler is going to pop then a bunch of registers. So that's why I need to push dummy handler frame, because the handler is going to pop stuff and then it's going to return. So the reason I'm pushing these dummy data frames is because they're going to be popped because of the design that I made and the events that are going to happen to this thread. Hopefully I answered that question. Okay, so now let's look at let's look at the compute pi example that we had. If you remember, I had this thread that would run compute pi, and it was like it had a while loop. While true, it would compute next digit, and then call thread yield. So on this user stack, I have the compute pi stack frame, and then I have the thread yield stack frame. Now, I mean, you can say p thread yield or thread yield. It doesn't matter. This is a library function that's going to then call the kernel yield, which is the system call, to context switch, right? So at this point, I'm going to trap the system library that I'm using. Let's say POSIX pthread is going to call the trap, which is a system call, and then we're going to call the kernel yield function. So at this point, when we switch mode, now we're using the kernel stack, and this kernel yield is probably going to, decide somehow, do I need to context switch, right? So we're going to put that all decision to whether or not we want to context switch in this run new thread function. So this guy, now let's look at the code for this guy, what it's going to do. So it's going to disable interrupts. Now, for now, accept this from me. We'll come back to this. Why do we need to disable interrupts? But in a sense, we're going to do something that needs to be done atomically. We don't want to be interrupted in the middle of this because we are going to change the stacks. We're going to choose the next thread to run. And if we change the thread, but we haven't yet changed the stack, and interrupt happens, then we're going to use the stack of the old thread while the new thread has been chosen to be a different thread, and that's bad. So we want to avoid this. We want changing threads to happen atomically because we're going to use the stack pointer of threads to handle interrupts. That's why I'm disabling interrupts here. So I don't want to be interrupted. I want to choose the next thread, start running it, and then I can be interrupted. Now, this is where I call the scheduler. I tell the scheduler who's going to be the next thread. Now, it could be that I'm the only thread in the system. So it could be that the chosen TCB is equal to the running TCB, the TCB that is running me. And in that case, I don't need to context switch. Let's say, in your system, you're the highest priority task and you called yield. Well, you're the highest one, so you should continue. There is nobody equal or higher than you, so you should continue. So yield doesn't do anything. But let's say that there is somebody else that we can context switch to. So let's say this chosen TCB is a different TCB than the currently running TCB. In that case, I'm going to change the state of this running TCB to ready because I want to context switch from this guy. So then I add this guy to the list of ready threads. Maybe it goes to the back of the list, but whatever scheduling policy you have, it's going to go to that list. And then what? And then I call this magic function that we've seen, thread switch. So now that I have a new thread to context switch to, I call this thread switch, I pass my TCB and this chosen TCB. So at this point, when this is called, the thread switch stack is a frame is pushed on the stack, and I start executing thread switch. Now I go inside while the stack pointer is pointing to the kernel stack of this running thread, and I get out of it while I'm running the thread switch in the context of the chosen TCB. So this function basically is not going to return at this point because we're going to pause here. We're going to context switch to someone else. Now, the magic is the return address where we want to return from this guy has been pushed on the stack. So here I have the return address of this next line. Next time I context switch back to this thread, I'm going to continue from the next line. What should be the next line? Can you guess? When we context switch back to this thread that we just context switched from, the next line should be, okay, now I'm running again. I'm back running because somebody context switched to me. So now my state becomes running. I might want to do some cleanup. For example, I might want to know how long I was, suspended or in the ready list or whatever housekeeping you want to do. And then you enable interrupts and you return. Now, let's look at an example. So let's say I have this code, A calls B, and B is basically a true while loop. It's an infinite loop that calls thread yield. Now, let's say I have two threads that are running this code. So let's look at thread 1. So there's thread 1 and thread 2. Both of them are calling the same code, or they're running the same code. Let's start with thread 1. So it pushed a stack frame for A. Then it pushes the stack frame for B, which has the while loop. And then it has the thread yield. Now, thread yield is going to trap the kernel and start running the kernel yield function, which then in return will run the run new thread function, as we saw. And then run new thread is going to call the thread switch. What happens here is that we're going to just pause here. And when I say pause, I mean the stack, the user stack and the kernel stack are not going to change. So we're just going to take a snapshot of this. Nobody's going to touch anything from now on. And we're going to start going and running thread 2. So thread 2 also runs A, B, thread yield, kernel yield, run new thread, and then it calls thread switch. What happens next is interesting. We're going to go back to 1. And what are we going to do here? So we're going to pop this thread switch. Where are we going to go? We're going to go to the next line in run new thread, where we called the switch. And it's going to return. So we're going to pop that. Then we go to kernel yield. Kernel yield returns. We go to B, and B is going to again call yield, and this cycle continues. Okay, so to summarize, we talked about context switching between two threads and whatever is necessary to implement that. We had to talk about creating new threads because because of the way we designed the context switching. And then we saw examples of, calling system calls. It would be the same if you want to look at, for example, getting interrupted. Instead of system calls, if you get interrupted, the same stuff happens, right? So you're running your code, you get interrupted, you go to kernel, you push the handler, and then let's say at some point in this, let's say it was a timer interrupt, and timer interrupt is going off and telling you that you need to now run another thread. Then you run the run new thread calls thread switch, and at that point you context switch to another thread. And whenever you come back, you pop the thread switch, you pop run new thread, you pop the handler, and you go from where you got interrupted in that thread. So the exact same process. Okay, now next thing I'm going to talk about. So whatever I talked about so far was in the setting where we wanted to implement threads by kernel. So we wanted the kernel to support and manage our threads. So if one thread, for example, calls IO, then kernel decides which other thread to run. If timer goes off, then kernel decides which thread to run. So in this case, the kernel is managing the threads. It decides who runs next, what's the state of each thread, and so on and so forth. Now, if you have a process with 10 threads, from the kernel's point of view, these are 10 threads that each individually can get blocked. So if one thread in one process gets blocked, another thread in this process can run because they're kind of managed all by kernel. Now, to just remind you about the big picture, if you remember from the past, in our systems, we have a ton of threads, like really big numbers of threads. Now, why is this important? Because context switching between these threads takes time. Now, how often do we context switch between these threads? Usually, these are like take it or leave it. Something like, again, these numbers depend on what system you're talking about. But let's say something like, in an order of milliseconds, or in very advanced servers in orders of microseconds. Now, when you're context switching, the cost of context switching is about 3 to 4 microseconds, which is negligible with this one, right? Now, if you context switch between two threads that belong to the same process, oh, I'm muted. Am I muted? So somebody said I'm muted. Am I muted? If you guys can hear me, then please say in the live chat that you can hear me. Okay. Okay, so if you context switch between two threads that belong to the same process, it's going to be even faster. If you context switch between threads that are from different processes, it's going to be slower. Now, let me tell you what this exactly mean, because you might think, okay, the code that we just saw, it didn't matter if the new thread and old thread belong to the same process or not. We were running the same code. Why are you saying that the overhead of context switching depends on which threads I'm running? Now, the overhead of context switching is really not just the overhead of the lines that we just executed. So it's not just the execution of those lines. It's really about what happens after that, right? So in a system, so I have to take a detour. So you have a CPU and you have your memory. And you might think that, what is happening is, you go from the CPU to memory to get your data. Now, in reality, in real systems, that's not the case. I have a L1 cache, I have L2 cache, I have some other caches. So every time I want to go to memory, I first go to L1. If I can't find my data, I go to L2. If I can't find my data, I then go to memory. So I'm not going to go to memory all the time. Now, what happens if you context switch? Now, these L1 and L2, these are basically very small storages, but they're very fast. Now, if I was running T1 and I context switch to T2, now T2 starts accessing memory. So the content of L1 will change. It will have the data that T2 wants. And probably the content of L2 will change. And in worst case scenarios, I might actually end up pushing T1 out of memory because I might not have enough memory for T2. I might end up pushing T1 out. Now, if I context switch back to T1, now context switching code is what you saw. But after that, T1 is going to start running, right? So it's going to start running. What it's going to do? It's going to access memory. Now, do I have the memory? Do I have the data for T1 in L1? Do I have the data for T1 in L2? Do I have the data for T1 in my memory? I may or may not. Now, if T1 and T2 are from the same process, it's very likely that I have all those data in L1, L2, and in my memory because threads are going they belong to the same process, so they're working with the same data. So with high probability, I'm going to actually find my data in L1 and L2. So when I start running, I don't need to warm up my caches. My data is already there because the previous thread that ran belonged to the same process as I. But if T2 that I context switched to, and now I'm coming back from, belong to another process, with high probability, L1 and L2 do not contain my data. My data has been pushed out. Now I have to, instead of going to L1 and L2, I have to just go to memory. Now there is a chance actually that my data is out of even memory and my data is pushed to the storage, let's say to the SSD. Now I have to bring my data and then I have to fill up L1 and L2. So as you can see, the code that we run to context switch is the same, but when they start running, depending on who ran before, it takes time to warm up my caches to get my data close to the CPU so that I can, run with high speed. So that's why I have these numbers here for you. So context switching overhead is really about when I start running, do I have my data next to me or don't I have it? And I have to warm it up. If I have to warm it up, that has a cost because it's going to slow me down. If I have my data in L1 and L2 and memory, it's going to be fast for me to run. So now this is not the whole picture for you because in a multiprocessor, I not only have CPU 1, I now have CPU 2. and CPU2 has L1, and CPU2 has L2, and CPU2 has probably its own portion of the memory. So these are portions of memory. Unfortunately, I won't be talking about multiprocessors in SE. Unfortunately, please contact SE director and tell him to add a concurrency course before SE, so that when you take SE or students that come after you, I have raised the issue with the director, and I told them that in ECE, students actually first take concurrency, and when they take ECE 350, they already know threads. So I don't need to spend time explaining mutexes and semaphores and what is multi-threading, what is the problem with concurrency, what is race condition. They already know that. So I use that time to talk about more advanced stuff. I talk about real-time systems, I talk about multiprocessors, I talk about, at the end of the course, reliability. But unfortunately for SE, I have to cut all of that because I had to spend so much time talking about concurrency. But anyhow, so I mean, you still can go and watch the lectures for ECE if you're interested. But in the multiprocessor, each core could have its own portion of memory. This is called NUMA, so non-uniform memory access. So CPU2, if it wants to to access memory that is local to it, it takes less time than if CPU2 wants to read data from a memory that is not local to it. That's non-uniform. So these accesses are faster than these ones. These are slower. Now, if I context switch, if I was running T1 on this core, and now I want to run T1 on this core, then CPU2 has to access the memory that is not local to it to read the data for T1, assuming that the data for T1 is in memory, this memory 1. Then again, if I'm context switching across cores, it's going to add another overhead here. So, and depending on work set, it could actually be even more. I will talk about work sets when we talk about caches. But basically what it means is like how much data this thread wants, because I could have some of my data in the memory and the rest of my data could be in SSD. So if I have a lot of data, then the context switching, if I context switch to T2 and my data is pushed to SSD, and then I context switch back to T1, I will have to bring my data from SSD, and that takes a lot of time. So the overhead could increase by 100x. Now, the overall picture here is context switching is expensive, and how expensive it is depends on data, really, because it's all about accessing memory and how expensive it is to access memory. Now, so far, all the things that we talked about were this one-to-one model where I have a single TCB for any single user thread. Now, if this thread calls IO, I just suspend this and I go to this thread. I can do that because I have the TCB for each one of them. So kernel is managing all these TCBs, context switches between them, saves them. Basically, everything is done with kernel's supervision. Now, this is good because, you know, everything is managed by the kernel for us. And threads are kind of like independent of each other, the way they run. One of them could be suspended, the other one runs, the other one can be suspended, the other one runs. Now, the downside, however, to this is that it's expensive to have the kernel context switch for us. To show you, I guess I deleted those numbers. If you remember, I wish I had. Let's do this. Just as a reminder, if you look at, let's look at, I think it was in the concepts. Just a reminder, I should have included this slide. Sorry. Yeah, this one. So this shows you, if you remember, this was the cost of, for example, system call. So going to kernel is expensive. These green bars show you the context, the overhead of a system call, whereas the blue bars show you the overhead. So this is for, so this what the heck? So this one, maybe I should use this guy. So this one is a system call, and the blue one is just a function call. So you can see the overhead of going to kernel is high. It's orders of magnitude more than it's just a function call. So in this model, we're relying on kernel to do the context switching, to do the scheduling. And this means that kernel is going to add its overhead. And that overhead is basically, changing the mode, pushing those, registers to the kernel stack and then popping them and all of that. That takes time. Now, an alternative to this is user-managed threads. So we want somehow to make context switching to be a function call instead of a function that is kind of like a system call. For example, we want yield to happen inside user space. I don't want to go to kernel and context switch. So I want to write that thread switch in user mode. I want to run that in user mode. That way, I don't need to context switch to, I don't need to do a mode switch to kernel, save everything and push everything on the kernel and so on and so forth. And then kernel does that, and then kernel does another mode switch, and all of that has overhead. I don't want to do that. So in this user-managed threads, from the kernel's point of view, kernel keeps a single TCB for this entire process, user process. Now the user process creates its own threads. So inside user space, it creates TCBs, let's say, whatever you want to name them, inside the user space. And then it context switches between them. It schedules them, it manages them. Now this is a N-to-1 model. So for N threads, I have one TCB. So kernel is keeping a single TCB, and users are the ones that are managing the threads. So the user process creates threads, maintains their state, and schedules them. And from kernel's point of view, kernel is not aware of how many user threads there exists. Kernel has no idea you're running 20 threads or 10 threads or 2 threads or 1 thread. As far as kernel knows, there is only a single thread. Now, on the surface, this model is good because I can context switch between these threads just in the user mode. I don't need to do a system call, for example, to yield, right? I can yield inside user space. Now, what is the downside, though? Oh, before we go to the downside, first of all, a bunch of examples for those of you who are interested. I'm not going to go deep into this user-managed threads, but if you want pointers to search and find interesting stuff, just search green threads. And that should be enough for you to find enough pointers. on user managed threads. Now, if kernel does not know about threads, what could happen? Now, here is a illustration of what could happen. Now, this is how kernel is looking at these three processes, because kernel does not know, sorry, these three threads. Kernel does not know that these three threads exist. Kernel just is looking at this process as a single TCB. And let's say at this point, from the kernel's point of view, this process, this thread is running, right? This is the user process with single thread from kernel's point of view. Now, internally, this process has created three threads, and it's running thread 3. So it's running the code of thread 3. Now, let's say that thread 3 calls on, let's say that, the kernel decides to context switch and go and run another thread. So let's say timer interrupt goes off, right? And we interrupt this process, this thread, to go to another thread. So this thread, from the kernel's point of view, is going to immediately, we're going to just preempt it. So it's going to go to ready. Now, we didn't have any time to change the state of the internal threads. So if I look at the internal threads state, the state is running. The reality is that this thread, this main user process, is preempted, and now it's on the on the ready list. So in the TCB state, so this is from the kernel. This is just ready. Now, in the memory of this user process, if I look at the state of thread 3, I see running, right? In reality, it's actually not running because this process is not running. But this process didn't have a chance to change the state because it was preempted all of a sudden by thread. And the operating system is not going to change this because operating system doesn't know that it exists. So it's all internal to this process. Now, another example. Let's say that this thread 3 that was running, calls IO. So it runs open, for example, open this file. What happens is, from the kernel's point of view, all of a sudden, there's a system call. Somebody called system call. What do? I make this thread suspended. I block it because now I have to go and do IO, right? So again, this process becomes blocked, and internally it didn't get a chance to really change the state of this. Now, one thing to note here, which is very important, is one of these threads called IO, but I had two other threads here that I could have run, but I can't because operating system is not aware of them. Operating system sees a system call to open a file or to read a file or to write a file, and thinks that, okay, this thread wants me to open this file or to read it, so I'm going to suspend it. Operating system doesn't know that internally this process is running multiple threads and it has two other threads that it can run. Operating system doesn't know, so the operating system just blocks you altogether. Now, here is how this could be actually good. This last one is kind of the good one, where let's say, let's say this thread 3, calls on a mutex or a semaphore that you have implemented in, again, user space. Now, I still haven't talked about implementation of mutexes and semaphores and condition variables, but when we get there, we're going to see how we can implement them. And we will talk about kernel implementation, but I will also note that you can implement these in user space. Now, in this example, let's say I have mutexes that are implemented in user space, and let's say that this thread wants to lock a mutex that has already been locked. So without any need to go to operating system, the process could make this guy blocked and context switch to another thread, all in user space, without any need to call any system call, to go to the kernel and ask kernel to context switch for us. It could all happen in user space. So this is where the performance of this model comes. And this is where the downside is. The downside is I might have a bunch of threads that I can run, but because the kernel is, suspending me, I don't get to run it. This is another example, right? Let's say, the kernel decided to context switch. I don't get a chance to context switch to my own threads. I have to now context switch to the kernel context switches to another process or another thread that is independent from me. So my threads are not going to compete with other threads in the system because the operating system doesn't know about my threads. So in a sense, all these 3 threads are going to be treated as one thread by the operating system, and that could be disadvantage. That could be a disadvantage for me, especially if I'm running on a multi-core system. So if there are multiple cores in the system, the operating system has no incentives to put one thread on 3 processors, because one thread only needs one processor. Even if this thread has 3 threads inside it, because the kernel is not aware of it. So even if I have a system with 4 processors and the other 3 processors are idle, I might be not given a chance to run on them because the kernel doesn't know that I internally have threads. So to put all of that together, the downsides of this user managed threads is that you cannot really take advantage of multi-core, and when one thread blocks, all threads block, so it's not that good. Now there are ways to kind of like make up for these. Again, I'm not going to go deep. I'm going to just give you a pointer. If you're interested, you can look it up. So there is this initiative that got some traction called scheduler activations. So this was proposed to support this M to N or N to M model. So M user threads mapped to M kernel threads. So basically your user process talks to the operating system, and instead of just getting one TCB, it requests for, let's say, 3 or 4 TCBs. And then it manages those, like kernel is managing those TCBs, but the user space is the one that maps internal user threads to these TCBs and says who runs on each one of these TCBs that I got from the operating system. And then operating system has to talk to the processor. That's why the scheduler activations is there. So we use things like signals, up calls, that operating system sends messages to the user process. For example, if one thread calls IO, instead of blocking the entire thread, the operating system sends a signal to the user process and says, seems like one of your threads called IO. Do you want to be blocked or do you want to schedule another thread? So operating system gives a chance to the user process to run another thread. So this is called a scheduler activation. It allows, again, as I said, to allocate more than one TCB to this process, and then the user process is the one that uses those TCBs, decides which user thread to run on those TCBs. Now, this kind of solves both of these problems, right? Because I can now assign each TCB to a core, so I can use the multi-core. It also, takes care of these blockings. So if one of my threads becomes blocked, then I get a signal, this activation, that I will then have a chance to run another user thread. So again, I just talked about user managed threads in 3 slides, 3 or 4 slides. I believe there are a couple of pages in the book talking about them. But it's really a very interesting area. I believe next term you're going to take 326, if I'm not mistaken. I don't want to. Is it CS3 CS326, if I'm not mistaken? Give me a second. CS326 URL. Yeah, you guys help me. Anyhow, there's this like concurrency course that you will take next term. If I'm not mistaken, the instructor of that course actually, for his research, does a lot of user managed multi-threading. So I'm just telling you that this is an area that is deeper than these 3 slides. So you could actually do research in this. So I'm going to move on from this. Now let's do a classification of operating systems, and I'm going to use 2 axes for this classification. The first one is how many processes does the operating system have? One process or multiple processes? And the other one is how many threads per process? One or many? Now, 1.1 is basically early MS-DOS systems or early Macintosh systems. They had a single process. That single process had a single thread. So everything was like there was just one thread running in the entire system, and that thread was doing everything. Now, this having one process and many threads is very popular in embedded systems. So the one that you're actually implementing right now, so your RTX is kind of like this. You have a single process or a single address space, and inside that you have these tasks. So your tasks are kind of like these threads, and some of these are kernel threads, some of them are user threads, but you have a bunch of threads because all of them kind of have access to the entire address space, right? So this basically is where we are in this course, right? Oh, okay, so it's CS343. Thank you. So CS343. Oh, are you sure? That's the. Oh, I have to put a URL. Yep. Thank you. Who's the instructor? Yeah, Peter. So if you go here, he's working, if I'm not mistaken, on these user threads, the user managed threads. Yeah, so like you can sort of see, I'm not suggesting that this is exactly what I just talked, but if I'm not mistaken, as far as I know, he's at least interested in user managed threads. So thank you for mentioning 343. And again, so the underlying the takeaway is that these user managed threads are actually bigger than these 3 slides that I talked about. I just gave you pointers. If you're interested, go and look it up. Okay, so coming back to what we were talking now, the traditional Unix systems were in this area that there were a bunch of processes, but each process had a single thread. And most of modern operating systems are here, many processes and many threads. So this would be Linux, Windows, OS X, basically all the modern operating systems, kind of general purpose operating systems are here. They provide processes, and each process has multiple threads. Okay, so that's that. Now I have 3 minutes left. Should I get us started? Or yes, I'm gonna just go a little bit, and probably won't be able to cover much, but let's set the stage for Thursday. Now, in the previous slide, in the previous lecture, we were talking on this layer. We were talking from the programmer's point of view. So we talked about, this is an example, we talked about bounded buffer, for example, right? So here, we talked about concurrency and what multi-threading means. Now, in these lectures from the previous lecture and today, we talked about how operating system can implement and provide support for multi-threading and concurrency. Now, if you remember, when we were talking here, we talked about mutexes, semaphores, and monitors. And these are synchronization objects. These are the things that the programmer uses to write its code. Now, we're going to now see how we can use primitives like load and store, disabling and enabling interrupts, and test and set, basically load, modify, and store operations, to implement mutex, to implement semaphore, to implement monitors. So this is the part 3 of these lectures, where we're going to talk about implementing synchronization objects. Now, I certainly cannot go further because I only have 1 minute left. So yeah, so I'm going to pause here. On Thursday, hopefully we start from here and we talk about how we can implement mutexes in kernel. So I have one question here. It feels like we developed this whole kernel structure just to retrospectively realize that it's inefficient. How do we know that this is the best way to do things? Now, I want to say, this is really good question, actually. Right now, in the operating systems community, and let's be real, even in the industry, there is a push to bypass kernel. Now, go and search, for example, kernel bypassing networking. If you are interested, just search kernel bypassing networking. And you probably will see a lot of stuff here. People are now looking at ways to bypass kernel to get more performance, because anytime kernel is involved, anytime we have this mode switch, we need to pay a cost. Now, you might say, okay, what the heck, like this question is asking. So we did all of this to then bypass it. And my answer to you would be, what do you care? Do you care about privacy, security, isolation, or do you care about performance? Now, most of these solutions that bypass kernel, they mostly have security, privacy, and isolation problems because there is no way that you could provide those without isolating them using kernel. And that was the whole point of having kernel. Now, there might be cases where you're like, I know my system, I know my users. For this particular system, I don't need kernel involvement, and I'm fine with bypassing kernel. But for I don't see, general purpose kernels to go away anytime soon. We might redesign components, but these solutions that kind of bypass the kernel, you have to know what you're trading off. You're trading off isolation that you get, privacy that you get, security that you get by having the kernel do this for you. You're trading that off with performance. So it's not like, is this the best way to do things? Because the best way of doing what, right? If performance is your concern, then probably this is not the best way to do it. If isolation, privacy, and security is your concern, then probably this is your best bet. So very good question, very timely, and there is a lot of debates. There is a lot of stuff going on today with this regard. So I guess I leave it there. Now, last thing I want to say is, still we need to understand all of these basics if we want to do anything, more advanced, right? So that kind of should give you the peace of mind that we're not wasting our time looking at how things are done today, because that could teach us what we could do in the future. And if we don't know what's the state of the art today, we might not be able to push it in the future. Okay, so with that, I end this lecture. Thank you for those of you who attended the lecture, and thanks to those of you who are watching. Now that you're taking in-person classes other than mine, please take care of yourself, be safe, and talk to you on Thursday. Bye-bye.